Only 13 has joined in the class, but let me start with some review of the previous class. So in the last class, we have covered some topics of section 4.3, that is routing and forwarding table, how a router decides on which outgoing port the packet will be forwarded based on the destination IP. Then also we have seen what are the different fields in a IP datagram or packet. There are source IP and destination IP. There are some other fields that are used for fragmentation. We have also covered fragmentation, which means uh, when a packet needs to be fragmented because of the limited capacity of a particular link. So when network layer forwards the packet, maybe that particular link cannot carry the entire packet at a time. So network layer needs to divide the packet into smaller fragments. Each fragment is a separate packet with its own header and travels through the network. And in the destination, the receiver reassembles all the fragments to the original packet. So that was the concept of fragmentation. We will do some hands-on works today. And also, I have given you some basic concepts of IP version 4 addressing for those who are doing computer network lab. This will not be a big problem for them. This will be easy for them. But for those who are not doing the computer network lab, you have to go through the basics of IP version 4 addressing so that we can use that concept in routing or forwarding table. So that's why I have given you some basic idea about IP version 4. It's a 32 bits address. It has 4 parts, 8 bits each, and then each part is represented as a decimal separated by a point or dot. And there are exactly 2 parts in every IP address. One is the first part is the network part that identifies a particular network, and the next part is the host part that identifies a particular host under that network. And to work with these IP addresses, we have to understand class A, class B, and class C. The first 8 bits decide actually about the class in IP address. So whenever you see an IP address, you see the first octet value, and you can decide whether it is class A, class B, or class C. And based on that, by default, you can decide 8 bits of network in class A, 16 bits of network in class B, and 24 bits of network in class C. But this can vary. We will see some examples. When we do subnetting, that means we borrow some bits from the host part and add to the network part. By those bits, we divide the network into smaller groups. In that case, this default number of network bits will be changed. But in every case, we need a network. What is a network address? When we set all host bit to 0, that will not refer to one particular host. That will refer to all the hosts within a particular network. So that is important for routing, because routing entries, router table contains only network addresses to accommodate all the hosts in a network using a single entry in the routing table. And then from a network address, we can calculate the host range using the combination of excluding all 0 and all 1 in the host part. This will represent the host range. So these are the things we have covered in the last class. Anybody has any questions before we can go to our next topic? We'll do some hands-on examples, but before that, we will cover one more concept, that is network address translation. Then we'll go to hands-on. And also remember that Remember that we will have an in-class assignment in the next class, that is Sunday 9th May, and the syllabus will be section 4.1 and 4.3. Is it clear to everybody?
Yes.
Okay. So now, before I go to hands-on examples, let me first cover the concept of network address translation. That is also part of section 4.3. So before going to NAT, we have to know there are two types of IP addresses, because in IP version 4, addresses were being exhausted too fast. So they have introduced a concept of private IP block and public IP block. Public IP is, as usual, it is worldwide unique. So no two hosts in the world can use the same public IP. The concept of private IP is anybody can use that private IP. It doesn't matter. Any number of organizations can use the private IP block, and they can if there is no connection between them, the networks, they can use the private IP block. So one more thing here, let me network address translation, that is actually NAT. To understand NAT, we have to understand private and public IP addresses. So public IP addresses are worldwide unique, and private IP addresses actually are unique only in a LAN, in local network. Okay, so why this private IP was brought in? Because to preserve the IP addresses, because it was being exhausted too fast, and already there are very few number of IP version 4 addresses. So that's why we have a new version of IP address, that is IP version 6. But in this course, we will not cover that much. We will mainly focus on IP version 4. Now, for private IP block, private IP introduced to preserve the IP address. Okay, preserve the IP version 4 addresses. As I have said, that IP version 4 addresses became exhausted so fast. So if we have only public IP, we always need to assign the public IP, so IP will be exhausted more and more faster. So using private IP block, in each class there is a block defined like 10.x.x.x. That means if the first octet value is 10 in class A, that is reserved for private IP. So if you use 10 in the first octet, then you can actually use that as a private IP. Similarly, in class B, the block that is defined as private IP is 172.16.x.x to 172.31.x.x. So that is class B. And for class C, There is only one block. There is 192.168.x.x. Okay. So NAT is covered in your computer network lab.
Yes,
Those who
sir.
are doing
More
the
or
lab.
less. Yes, sir.
Okay. Okay, fine. But for those who are not doing lab, just I'm uh, giving you the basic concept. So this private IP you can use without any registration. That is the advantage. So any number of organizations can use the same block as long as they are not interconnected. That is the advantage. But it is fixed that private IP will not be routed through internet. So whenever a packet goes to an ISP with source or destination IP as private, the ISP will by default drop the packet. Using private IP, you cannot browse the internet. So that is the rule, but we need to use the internet even after using private IP. So that's why NAT has been introduced. The idea is simple. The idea is, since private IP cannot be routed through internet, so whenever any client from my network connects to the internet, it is my responsibility, organization's responsibility, to convert that private IP to a public IP so that that can travel through the internet to the destination. This concept is called network address translation. So you can see the idea here. On the right side, you can see a local network, and you can see the IP is 10.0.0. That means 10.0.0/24. That means network part is 24-bit. So this represents the network part. Since it is 10, it's a private IP or public IP?
Sure.
Private.
Private, because this is defined. This is already defined. If you say 11.0.0, private or public?
Public, sir.
That is public. Only 10 in class A is private. But when anyone from my network tries to connect to internet, suppose google.com, and if I don't implement NAT in my router, then it will be, maybe it will be forwarded to the ISP and ISP will block. Simple. So you cannot browse internet. So what we will do, datagrams with source or destination in this network has a private IP, so it will not be forwarded by the ISP. So it is the responsibility. Suppose this is the router, we call it border router, exit router. This is the last router from which packets go to the ISP. So we have to implement NAT here in such a way it is connected to the internet, and before leaving this router is configured with NAT. So router will transfer the private IP to a public IP. Now where this public IP will come from? It must be rented from ISP or from authorized agent. You can rent one public IP, you can rent 10 public IP, you can rent 100 public IP. It's up to you. So you must define that in the router. That you will do that in the computer network lab. So we are not going to the implementation, we are just going through the concept. So all datagrams leaving the local network, in this case routers outside port IP, you can see 138.76.29.7. This is a private public IP, right? This is a public IP. Which class this is? 138?
The class B, sir.
Very good. Class B, 128 to 191. You have to keep it in mind. That is class B. So since it is a class B, and in class B we know only 172.16 to 172.31 private IP. All other is public. So this is a public IP rented from an ISP, assigned to router's port, and this is the only public IP that is used here. So all datagrams leaving local network have the same source NAT IP address, and but different source port numbers. Okay, why different source port numbers? We'll see. So this is the idea. So whenever any data going through my router to the internet, my router, if we implement NAT, it will convert private IP to public IP that we have configured earlier. That is the idea. This is already covered. So these are the advantages. One thing you can just think using only one public IP, you can create more than 60,000 connections simultaneously, theoretically, because we will see port number is 16-bit, and using one public IP, you can change the port number so that we can differentiate the connections. We can create more than 60,000 connections. And there are some other advantages for NAT. We can change the addresses of host in local network. We don't need to inform the ISP because that is hidden from the ISP. Also, you can change the ISP without changing the addresses of devices in the local network. So these are the advantages. And one inherent advantage is, since my internal network is hidden from the outside, nobody can access my network or any host with a private IP. So that is an inherent security advantage of NAT. So how it is implemented, I have already told you. Whenever a packet goes through the router, it converts the source private IP to a public IP that is configured. And during the process, see this example. This is a very good example to understand NAT. For example, host 10.0.0.1 sends a datagram or packet to 128.119.40.186. That is a server in the internet. So is it a public IP or private IP? 128.119.40.186.
So it is public.
Right, it is public. So like google.com or like facebook.com or like any server that is publicly available, we are browsing from, for example, from a lab in EUIU, or you are at your home, you are browsing the internet, and you are definitely under NAT. How you can make sure? Just go to your PC, go to the command prompt, and you can give some command like ipconfig. You can see the IP address that is assigned to you, and you can just see whether it is a private IP or it's a public IP. Definitely, you will, most of the cases you will see it's a private IP. So that means you can browse internet. That means you are definitely inside the net. So how it works? So similar concept, a user sitting on 10.0.0.1, this is a private IP, browses 128.119.40.186, that's a server in the internet with port number 80. That means what? That means request is going to web server, right? This is a web browsing using HTTP. So you can see in the packet, source 10.0.0.1, and there is a port number. Definitely we know whenever a packet is generated, it is generated from a segment. So definitely there is a source port number, there is a destination port number. So you can see source IP is this 10.0.0.1, source port number is 3345, and destination IP is 128.119.40.186. that is the server, public server, with destination port number 20. Now this will travel through the router because the destination is outside the network, outside our local network. So it will definitely forward it to the router. What router will do? Router will maintain a table. This is called NAT translation table. This is not routing or forwarding table. This is a different table where router will store the information. Why? It will be clear. Just shortly, it will be clear. So whenever it sees router C, because we are assuming NAT is configured here with a public IP given and outside 138.76.29.7. So whenever it gets a packet, it sees that, okay, the source is a private IP. So what router will do? Router will convert like this. You can see only source IP and source port numbers are changed. Destination and destination port number is not changed. Why? Anybody? Why?
Destination the public IP.
Very good, very good. Destination is public. So any public IP can travel through the internet, no problem. But private IP, the first ISP router will block because of the system. This is the rule. So my router will do what? It will change the source private IP to the given public IP. What is the given public IP? The IP address assigned in the router's outgoing interface. But it can be in a different way. I can rent 10 public IPs and I can configure all public IPs in the router. So router will know any public IP out of those 10 addresses can be used. But in this example, only one public IP is used for simplicity. So simply the source private IP is converted to the given public IP. But why the port number is changed? That is the question. It could have been kept same, right? 3345. Do you agree? If I keep the port number 3345 same, it could have been, right?
Sir, এই পোর্টটা তো আমার প্রাইভেট না।
Port is not private or public. Port is actually used for 16-bit number. Okay.
Sir,
Okay.
is it specific to my router and my computer configuration only?
Yes, but okay, I will make it clear. Just keep the question in mind right now. Why we have changed 3345 to 5001? That is my question, but the answer will be given just after a few
বিষয়টা
minutes.
কি যাতে আমার মানে আমার ল্যান যাতে এই পোর্ট নাম্বারটা নেক্সট আবার ইউজ করতে পারে?
Not exactly, but something related to the concept. Okay, just I am coming back, just after completing the example. So step 2, this packet, you can see the source IP is changed and this will be forwarded to internet. Doesn't matter how many routers in the middle, it will reach the final destination of the server 128.119.40.186, right? Now in the process, router stores a LAN side address like 10.0, what it has changed to what IP, public IP and port number it has changed. Later we will see there will be many entries in this NAT translation table. Why? It will represent the number of simultaneous connections from my inside network to the internet. Why this table is used? Okay, now server received the packet. Now server will respond, right? So what will be the change? Just source will be destination, destination will be source, because server sees the request coming from router's public IP, right? Server will not be sure the request is coming from 10.0.0.1. So server will send the feedback to router's interface. Now see, the source in step 2 will be the destination in step 3. The destination in step 2 will be the source in step 3. Is it clear?
Yes,
Just
sir.
you can assume there is a server in the internet. I am not showing the server here. Now again, this packet will come to the router's outside interface again. Router will receive the packet. Now router must go to the NAT translation table because it received a packet with destination that is the IP of the router's interface, but there is no host with that IP. So it will go to the NAT translation table to see which local host should receive this packet, right? So it will match with this destination. Okay, it says that okay, the local host that has requested is 10.0.0.1 with 3345 port number. So it will send back to the packet to that particular host. Now let me make it clear. Should this host know that there is a translation happened in the middle? If
No,
you
sir.
see step 1 and step 4, you can see just source and destination reverse. So host requests to 128.119.40.186 and host receives a response from 128.119.40.196. So there is no way for the host to understand that there is a translation happened in the middle. So for host, it is fine. So you are browsing from home, you are browsing from UIU lab. As a user, you will see nothing. It's a transparent. But now the router in the middle changes 2 times. First private to public and then public to private to make sure that users using private IP within a LAN can browse to the internet. So that is the network address translation. Now the question, in fact, the answer to the question, why we did not keep 3345, we have created a new port number 5001, right? That is the question. If we keep 3345 here, will it be a problem? For this example, I think there will be no problem,
Yes, sir.
because
For this example,
no
there will be
problem.
no problem.
But now assume,
Sir, same port can be used by the other PC.
right. That is the point. Good. That is the point. Okay. Now assume 10.0.0.2 is communicating with the same server. How many users communicates with Google?
Billions.
Many users can simultaneously
Million.
communicate to Google in our UIU network. Okay. So assume 10.0.0.2 sends the same request to the same server. Now what will happen? There will be another entry in the table, right? 10.0.0.2, and for the sake of the example, assume it could be different, but assume the same port number used by host 2. It can happen. Two hosts can use the same port number, right?
Yes,
But
sir.
two applications in the same host cannot use the same port number. So if you think about 10.0.0.1 is another application is communicating, that must be different, but that must use different port numbers other than 3345. But if we think about 10.0.0.2, a separate machine, separate host, it can use a different port number, it can use the same port number. To understand our concept, we assume this will use the same port number. So there will be another entry here, 10.0.0.2 and then 3345, right? Now for the second entry, what will be in the WAN side? WAN side means internet side. Public IP is same, right?
Yes, sir.
So 138.76.29.7. If we use the source port number, both entries will have the same port number, right? On the WAN
Yes, sir.
side, 3345. Now when two different connections sends two different packets, will it be a problem for the router to decide which host should receive that particular packet? Because 10.0.0.1 should receive its own packet, 10.0.0.2 should receive its own packet. But if you keep the source port number as it is, and there are two simultaneous connections with the same port number from two different hosts, then you will face a problem, because which packet should send to which local host, because both has 3345. You get the point?
Yes, sir.
Yes, sir.
So that is the problem. And another reason, if we use one public IP, so in that case we can use only one connection, right? So use one public IP, you can create only one connection. If we keep the source port number same, that is not scalable, that is not good. What router will do? Router will store in its NAT translation table, it will store the local net IP and local port number also, but it will create its own port number. Why? Now if there are multiple hosts from local network communicating with the same server, router will produce different port numbers. So for the second one 5002, for the third one 5003, but every time it is using the same public IP. You get my point? So now
Yes, sir.
many different connections can be simultaneously made, and whenever replies come, now there is no problem, because each reply will have different port number to the router. So router has the corresponding entry, so router will know which local host it must forward the packet. Now the problem is solved. And also, since router is generating a new port number is 16-bit, so how many values can be generated? From 0 to 2 to the power 16 minus 1, right?
Yes, sir.
That means using a single public IP, theoretically, more than 60,000 connections can be created, because some ports are actually reserved for a special purpose, but other ports can be used. So this is the idea of NAT. And when we use the port number to differentiate connections using the same public IP, we call it PAT, port address translation. So network address translation, port address translation. Is it clear now? So
Yes, sir.
router uses a port number for its own purpose, for the NAT only. But you can see this 5001 will not be in the return reply. Did you see here? This is
Yes.
3345. This is not 5001. This is 3345. So for the host, this is not a problem. Host sends with 3345. Host receives with 3345. No problem. But router uses its own port number to actually trace different number of connections. So that is the idea of network address translation. And for this, actually, there are some drawbacks or criticisms of NAT also, because router works in which layer?
Application.
Networks.
Network layer, right? Network layer. So uh, so router should not use port number, because port number is used in which layer?
Transport layer.
Very good, transport layer. So there are some criticism of NAT. Although router is using this port number not for application connection, right? It is using this port number to trace individual translations in its NAT translation table. And also, there is another violation of networking concept in NAT, because normally we have said several times, right? Source IP and destination IP will not change during the travel from source to destination. In chapter 1, we have also solved one example. Can you remember?
Yes, sir.
But MAC addresses will change in every link. But here we see in the middle, IP address is also changed. So that actually makes application development very complex. Some of the protocols very complex. So these are some of the disadvantages, drawbacks, or criticisms of NAT. But still, to use IPv4 effectively with private IP block, we must use NAT. And we don't know how many more years IPv4 will be existing with us. So we have to bear this network address translation concepts. Okay. Okay, I think we have completed the theoretical part. Anybody has any question? Now we will do some hands-on lab. Okay, in the workbook, we have some problems, but for the time being, let me do some examples. I am giving you some examples from my own, just to make sure you understand the basic concepts. Let us first do fragmentation, okay? Fragmentation. So for fragmentation, let us assume that the original packet or datagram, same concept, okay? Original packet size equals to 5,000 bytes, and assume MTU of current link. That means data link layer, or current link has MTU. For example, let us change, although it depends on a particular protocol on which it is being used. So let us assume it again 1600. Okay, 1600 bytes. And if we don't say anything, you will assume the header size, IP header. If we give, it is fine. If we don't give, then you will assume header size is 20 bytes. So now your question is, show the fragments with the required fields. Now we know that when we do fragmentation, we can think for every fragment. So you can write down like 5000 bytes total length equals to 5000 for the original packet. Okay, then ID equals to, for example, A, and then fragment flag or only flag equals to 0, and we know the offset will be also 0 because this is the original fragment, not
Yes.
original packet, not fragmented. Okay, now if you just calculate in this way, this is I think it will be easier for you to understand. First you have to do it like 5000 minus 20. So it is the total length. Just you can do rough on the left. So this is the original packet length 5000, then minus 20 is IP header, then you will find 4980. This is what? This is actually the data or payload of the original packet, and we can understand this data part must not be lost, must not be missed. Any bytes must not be missed. So these 4980 bytes must be distributed to different number of fragments so that MTU will be 1600. So since MTU equals to 1600, so data in a packet can be 1600 minus 20, right? So 1580. This is trivial, right? So also in each fragment we cannot send more than 1580 bytes of data. So now you can do some simple calculation. You can think, okay, I am sending 1580 bytes in fragment number 1. Okay, and then you just subtract. So after the first fragment, then we'll actually show the different fields. Just for the time being, let us do the calculation first. We have to transfer this 4980 bytes using MTU of 1600. So each packet will carry 1580. We'll see how many fragments we need. So after sending the first fragment, the remaining will be 3400, right?
Yes, sir.
So again you send another fragment, very simple, that is fragment number 2, and then divide, subtract. So it will be 20 and then 6
1820.
18, right? Oh, okay,
Yes.
right, 1820. So we will need another fragment. We can, in this way we can understand actually very fast how this is happening. We are doing it manually. Now, what are the remaining number of bytes?
240.
240. Now, see, this is less than 1580. Anything less than 1580 means this is the last fragment. So, but even if there is 1 byte remaining, you have to use a separate fragment. Although in that case, data will be 1 byte and header will be 20 bytes. But you have to send a separate fragment. So this will be the 4. So by this way, you can already see we need 4 fragments, right? Now what you will do, you will just put these values here. This is fragment number 1. So what we will do, length will be what? Length means total length. That means it is not 1580. It should be 1580 plus 20, right? ID will be same. ID will be same as the original packet, and then flag will be what?
1.
1, because this is not the last fragment, this is the first fragment. And offset will be, for the first fragment, offset will be 0. So this is fragment number 1. So fragment number 1. Then for fragment number 2, again we can like write this. So length will be again 1600, ID will be A, flag will be again 1 until we go to the last fragment, and offset will be what?
1.
Okay, for
1.
offset, no, offset is
Sorry,
always previous
cumulative.
data.
Cumulative.
Previous data, right? So it will be 1580 divided by 8.
8. Yes, sir.
So 960
So 197.5.
1.5. Fine. So you keep it 197.5. Don't worry. Sorry. Okay. 8 is just a value. Simply a value. We could say okay 1580 is the offset. Fine. But actually this, to store this offset value, there is a number of bits. You can see in the IP header, every field has a fixed number of bits, right? So to store 8 times larger value, this is the only reason. There is no other reason. So if we divide it by 8, we can store in that particular field of offset 8 times larger value. So that means it will accommodate larger number of bytes. That is the only reason it is divided by 8. Clear? So you will divide by 8 and then store that value. Now for fragment number 3, there will be another one, and I think we need to draw another one because we have seen there are 4 segments. Okay, now for the fragment number 3, again length will be 1600, right? ID will be what? A. Flag
Yes,
will
sir.
be again 1, and offset will be what? Offset will be 1580 plus 15. Always
8.
remember, offset will be total number of bytes sent in previous fragments. So for fragment number 3, how many fragments already sent? 2. So
sir.
you have to sum data or payload in those 2 fragments and divide by 8. Basically, this is 197.5 into 2, right?
Yes, sir.
Is it clear?
Yes, sir.
In
Yes, sir.
fragment 1, 197.5. In fragment 2, 197.5. So in fragment 3 will be 197.5. Actually, offset represents the starting byte of the current fragment. You can remember like this. So starting byte will be what? Fragment 1 size plus fragments 2 size. So this is the idea. And for fragment, last fragment, we see what will be the length? Anyone?
So
47.
40 plus
240 plus 20,
yes,
right?
sir.
So
Yes,
it will be 260.
60.
It is not 240, it will be 260, because always length is total length, that is data plus header. And then ID, same as A. Flag will be what?
Sir, 0.
Right. Now flag will be 0 because this is the last fragment.
Yes, sir.
The only use of fragment flag is 1 or 0 to indicate this is the last fragment. So receiver will know, okay, I have received the last fragment. I can start reassemble. What will be the offset? I can
into 3.
directly
Is
write,
of
right, into 3. So this is simple.
1980
So it
divided
will
by-
never happen. This 240 will come into the offset calculation. It will never happen. So the last fragment will contain less data, but that data will never come into the calculation of offset, because offset always represents the previously sent data, right? So you can, if you find the first offset 0, then the second offset 197.5, you can get the third one 197.5 into 2. You can get the fourth one 197.5 into 3. Clear, everybody? Any question?
সেখানে
So is
চারটা
it,
ফ্র্যাগমেন্ট কেন করছিলাম? এখানে কি বলা থাকবে কত
Which one?
পর্যন্ত করব? মানে ফ্র্যাগমেন্ট
As-
চারটা পর্যন্ত গেছি না?
oh, okay. Why segment is 4? That is shown on the left side. I have shown you some calculation, right? Also, you can decide on number of segments. You can also do it like this. Number of, sorry, not segments. It is number of fragments. See, segments are in transport layer. Fragments are in network layer. So segments and fragments are not same, although the concept is similar. How you can get the number of fragments? Can I say like this? 4980 divided by 1580.
Yes, sir.
This is the ceiling. Why ceiling? As I said, if you get the fraction, okay, somebody tell me what is the value, what is the result of this division? 4980 divided by 1580. Use calculator. What is the value?
So 3.15.
Very good, 3.15. So 3.15. Why we use ceiling? Because we definitely need to send 4 packets, 4 fragments, because 0.15 means some bytes remaining. You have to use a complete new fragment for that. Is it clear now why we need 4 fragments?
Yes,
You can
sir.
directly calculate, or you can show like this way. I have shown in the left side. Okay, here you can see every time I subtract 1580, that means this is fragment 1, this is fragment 2. So in this way we can also calculate, okay, how many fragments we need. Clear, everybody?
Yes, sir.
Okay. Okay, so let us now do one example on routing or forwarding. So suppose a routing table is given. Suppose a routing table is given as. So whenever we give a routing table, it is like it shows network address, it shows a subnet mask, and it shows next hop or interface. Okay, so whenever you have a routing table, there can be more information, but we can just think about this as this basic set of information. What is network address? For example, there is an address given. If I use one of the examples from our workbook, you can see this example number I am specifying. Just 1 second. Okay, so this is basically you can see exercise 2. So I am the routing table is not given here, but I am first, there is a diagram given. Just assume that we have a routing table given. So that is 143.89.60.192. One 143.89.160.192. Then it says /26, but /26 we can represent /26 as 255.255.255.192, right? /26 means 26 bits network. That means 26 bits will be 1 and remaining 6 bits will be 0.
0.
So if we take 8 ones at a time, 8 ones means in decimal 255. So 255, 8, 8, 8, 24. And in the last octet, first 2 bits will be 1 and rest 6 bits will be 0. So it is 192. Now, what will be the next hop? That will be given in the diagram or that will be given in the routing table. So in our example, in this case, next hop will be interface 2. Then there is another entry 143.89.160.128. It is given /25. So you can represent, I can give only /25 /26. You can convert to subnet mask, or I can give you subnet mask directly. But in this case, we are representing in both formats. So it will be 128, right?
Yes, sir.
Do you have class after 12:10?
Yes, sir.
Can I take 5 more minutes today?
Yes, sir.
Okay. Anybody has any problem? Okay, because we want to complete this example, I will need only 5 minutes
No,
more.
sir, you can take 5 minutes.
Okay, okay, thank you. So in this case, the interface, it will forward according to the diagram is I3, and there is one last network, local network, that is 220.32.19.0. Now, when there is no slash, no subnet mask given, no slash information given, that is no network bits given, how can we get the number of network bits?
So JTS 0, it ignored.
That means from
Yes,
class, right? From class.
Yes, sir.
Yes.
Sir.
So which class this 220?
Sir, class C.
C, sir. C, sir.
Right,
C.
class C. So since class C, although nothing given in the question, you can now assume like 255.255.255.0, right?
Yes, sir. 24
/20,
bit.
since it is class C. But if I specify here /28, you have to use /28. But if I don't specify, okay. Now this will be interface 1. So there is a routing table given. Assume the routing table says there are 3 different network addresses, possible destination networks. with slash number of network bits or subnet mask, and if a packet's destination IP matches this, then which will be the interface it will be forwarded to given in the table. So that is the basically routing table. There can be many more information, but this is the minimum information a routing table stores. Now let us go through some examples. The examples will be in the format like what will be, which interface the packet will be forwarded if the packet's destination IP is 200.32.19.201. Is it a valid IP or it's a network IP?
Valid IP.
Valid IP. So definitely in every packet there will be a valid IP in source IP and destination IP as in the network IP header. But we will use only destination IP to decide on the interface. So this is the destination IP. Now what router will do? Router will first go to first entry. Will it match? This is
No,
very
sir.
simple because
No,
one
sir.
for first octet is not matching. Then router will go to second entry, will not match. It will go to third entry, will match? Yes or no?
No, sir.
Simple.
Class. Yes,
It
sir.
is 220 and the given IP has 200. Although
No.
3219 same, but don't be fooled because the first octet, if the first octet doesn't match, there is no way the IP can match. So what will be the result?
So default to নাই এখানে।
Result will be discard, right?
Discard.
Discard or drop, anything you can write. If no entries match in the routing table, simply router will discard. And one possible option maybe in this case, one possible option may be here, like it is not mandatory, but maybe in the routing table there is one more entry in the routing table. We call it default, right? If default is given as the last entry, what would have been the result?
So default interface.
Right, default interface. So in case of default, there will be an interface given. So no packet will be discarded or dropped. So if there is a default in the routing table, no packet will be discarded or dropped. Okay, but to make it clear, don't be confused. We are using only this type of, there is no default in the routing table, so it will be discarded. Now another example. Anybody has any question? Okay, now if you do the second example, I think it will be much more clear. 143 89 160 197. Okay, first of all, how we will display this? I mean, how you will demonstrate this? Will you write only the answer? That is risky. If your answer is wrong, you will get 0. If your answer is correct, you will get full marks. So yes, Imtiaz, any question? Imtiaz? Okay. Imtiaz, do you have any question? Otherwise, please mute yourself. Okay, so in any case, when you display, you can display in this way. Like 143, 89, 160. You can see in the routing table, it can match the first 3 entries very easily, right? All are decimal. So you don't
Yes,
need
sir.
to think much. But there are 2 entries with 143, 89, 160, right? So you have to first decide which value you need to convert into binary. So which value we need to convert into binary?
Sir, last 8.
One
The
nine-
last part,
Last
the
two,
last
last
part,
two, last
right? But you don't need to convert to binary the other 3 parts. So what you will do to display, to demonstrate in this type of question, also for your understanding, you will convert 197 to binary, and it will take some time to actually calculate this, but you have to be first to calculate binary to
Yes, sir,
decimal,
sir.
decimal to binary. Okay, so what
Yes,
will
sir.
be the binary value?
স্যার 1 1 4টা 0 তারপর 2টা 1
Okay, 11000011. Very good.
Yes, sir.
Now this is the destination IP address, but we have to match with what? We have to match with each entry in the routing table. So again, what you will do, since you know, okay, last octet only needs to be matched, so we need to convert the other octets. So
Sir,
yes,
sir, I got 101 first. Chapter 0.
yes, maybe 101.
So
right,
so
right,
so
right.
101 স্যার
Yes, right. I
5 হবে
yes,
4
yes, 101.
192 plus 5
Yes, thank you. But to match with each entry, again you have to convert each entry on only the last octet of each entry into binary. So 192, it is very simple, 00000, sorry, 00, and then 128, 1000000, right? And then you don't need the last one for the time being, but you have to make sure, see, for the first entry to match, you have to match these 2 bits, right? For the second entry to match, you have to match only to the first bit. Is it correct?
yes sir
So as we said in the last class, when it says /26, exactly 26 bits must match. So first 24 bits, it is decimal, so it is very simple that we can identify all 3 parts matched, but only the last part we need to convert to binary and then the match. Now for the given IP, here, is it matched with the first entry?
yes sir
Will it match with the second entry?
yes sir
Yes.
Sir,
But yes,
Co-
so it is matched with more than 1 entries, right?
yes sir
Although according to our theory, it will only take the longest prefix matching, and the more entries matched, and the entry with more bits matching will come first. So the if else if will also work, right? So all
Yes, sir.
things will work, but theoretically you have to keep in mind, whenever this type of, I can ask you questions like explain. In that case, if you just only write interface 2, that will not be enough. You have to write the result will be interface 2 because of, this is the explanation,
yes sir
longest prefix
match
match. Okay,
Match.
longest prefix matching. So you can also explain like this 26 bits match with interface 2 and 25 bits match with interface 1. So you can also write like this to understand better. Since interface 2 matches with more number of bits, the result will be interface 2. So I think all possible answers I have already covered using these 2 examples. So any routing table, any IP address I give, you should be able to solve, and you should be able to demonstrate your calculation in this way. Any question, any confusion, anybody? No? Clear? All clear?
yes sir
Very good. So next class we'll have an in-class assignment, and before start of the in-class assignment, I will show you one example with NAT. Although the example is shown today, but I will do one example, then we will go for in-class assignment. Okay, just let me take your attendance very fast. So be alert. I will call Abdullah Al Rifat,
Yes, sir.
Inamul Haq,
Present, sir.
Imam Reza,
Present, sir.
Rokunujjaman Khan,
Yes, sir.
Laila Ishrat, Farah Farzana.
লাইলা ইসটা চ্যাট বক্সে মেসেজ দিয়ে
Okay,
গেছে
okay. Farah Farzana, Fazle Rabbi, Priyobroto. If
তো চ্যাট বক্সে মেসেজ দিয়ে গেছে
okay, okay. Ifat Rafsan,
Yes, sir.
Ali Ahmed,
Yes, sir.
Kaushik Devdash,
Yes, sir.
Khurshida Jahan,
Yes, sir.
Samir Ahmed,
Yes, sir.
Mahmudul Hassan, Fahim Shakil,
প্রেজেন্ট স্যার
Abu Sajjad,
Present, sir.
Nibirujjaman, Sadman Shakib,
Yes, sir.
Adnan Kobir,
Yes, sir.
Taki Yasir,
Present, sir.
Shahadat present,
Yes, sir.
Rakibul Islam,
Yes, sir.
Al Shahriyar, Tanvir Hassan, Sakib Hussain,
Yes, sir. Yes, sir.
okay, Sakib Hussain present, Al Shahriyar present, Tanvir Hassan, Mashuke Alam present, Sabbir Sarkar,
Yes, sir.
Abrar Sadiq,
Yes, sir.
Ishtiaq Ahmed, Mufail.
Yes,
Ishtiaq
sir.
was present, I think. Okay, Mufail present. Mahfuzur Rahman Sifat,
Yes, sir.
Shafiqul Islam Niro present. Amanta
Yes,
Hussain,
Present, sir.
Abir Reza,
Present, sir.
okay. Jahidul Islam,
Yes, sir.
okay. Khalid Ridwan, okay. Shahariaz,
Present, sir.
Tahmina Tanjin present. Muhammad Mahfuzur Rahman,
Yes, sir.
Fazila present. Ashrafun Nahar,
Present, sir.
okay. Shifa Chaudhuri, Misbahul Alam,
Yes, sir.
Yasir Arafat present. Sudip
Present,
Sarkar,
sir.
okay.
Sir,
Sudip
Yasir
Sarkar,
প্রেজেন্ট স্যার প্রেজেন্ট স্যার
Abdur Rahim,
Yes, sir.
Miraz Farooq, Abu Abdullah, Khandokar Shravan, Shah Alam, Imtiaz Hussain,
শাহ আলম স্যার হচ্ছে শাহরিয়ার আলম না স্যার অনেক
181168,
জি স্যার ওর হচ্ছে নিতে সমস্যা
okay. Rifaz Nahian,
Yes, sir.
Kamrul Islam Tushar, okay. Dihan Pathan, Muhammad Abu Kibriya, okay. Dihan Pathan present. Muhammad Abu Kibriya, Bidhan,
Yes, sir.
Shakhawat.
প্রেজেন্ট স্যার
Okay, thank you very much. See you on Sunday.
Assalamu alaikum, sir.
Wa alaikum assalam.